So yeah, we're going to finish these slides, start some new ones. This will be the last new content for the semester week, because next week is going to be the week before finals week, and I like to do a review for that. So we're going to do final review stuff next week. And so this is the last stuff that could be on the final. Last stuff that needs to get into your brain that's new. So that's exciting. So it's weird to have a Tuesday. We had a Tuesday holiday as well. And so usually I get one more semester out of my 41s. So you're missing out on a little bit of stuff. Usually I teach like Python and Java, but there's no time for that. Sorry. Come to office hours if you want to learn any of those things. I'll teach them to you. But yeah, I think if we're good to get started, let us take attendance. Boop. So tell me you're here. And then, yeah, it'll just be finishing up that stuff today. Any questions before we do that? All right, so we learned about tries. We learned about Huffman coding, which is the idea of combining a priority queue with a binary try. And we've called that a Huffman tree once we build it. So yeah, we've made a bunch of cool types. We've got the H-tree nodes down already. That was what we implemented last time. I got way too many slides open. That one, we got that one. So where we were last time was this Huffman coding.h file, where we lazily implemented all the stuff together. So we've got in our Huffman trees, we're going to treat them like H-tree nodes. And so we put all the things that any node could ever want to have, any interaction we'd like to make with any kind of node, up in this base class. And all the nodes, no matter what. So the leaves, they hold characters and frequencies. The internal nodes hold frequencies and left and right children. Right? So that was the difference. So frequency is the thing that's in common, so we make that a protected thing. And then we still need the ability to do everything else that any kind of node could do. So like get the frequency, we do that. We'll use a virtual method that tells us if we're a leaf or not, because that'll tell us if we can call which getters we're allowed to use. So like get character would work if is leaf returned true. That's how we know we were a leaf. Because we're going to treat everybody as an H-tree node star, because we're going to put a bunch of different kinds of nodes, like multiple different kinds, internal nodes as well as leaf nodes into our priority queue. So we need to treat them like the base class. So that's what's going to happen, because we're going to make a priority queue of H-tree node stars. We have to do that. So if it's a leaf, we'll call isLeaf and use get character. If it's not a leaf, if it returns false still, we can use the get left and get right to get H-tree node stars out of this deal. So yeah, we know what leaf nodes have. The extra thing is their character. They override the things they need to override. Internal nodes have lefts and rights for real, and we override their left and right getters to actually give those things back. So that's what we've done so far. And now we want to do the rest. We want to do the actual compression. So let's go to the textbook. Learn.zybooks.com. Boop. Right now, what do we got here? Is it in algorithms? There it is. Huffman compression implementation. So just like everything else in your book, there's code for all this. So here's the code that builds the character frequency table. You give a string. The string is the file you'd like to compress. We're going to keep track of how many times we see which characters in like a hash map or something. But we'll use like an unordered map maybe. That will work, or just a normal map. You get there. So that's that one. We need to build a character frequency table. We need to build the actual tree, right? So first we need the frequency table. Then we make a priority queue. And we go through it as long as we can, like while we have things, we combine them, making an internal node. Each time we combine a left and a right, we add their frequency to make a summed frequency, like you've seen these. And then to actually like encode something, we need to get back the codes for everything, and so that's a recursive function. We'll make in a method. So all these things exist for us, and here's the compression and even decompression. So there's a bunch of code. We will use this code, all right, because that's the rest of this. Everything else is going to happen in this Huffman coding class. That's going to do the compression for us. So like the constructor is going to take the file as an IF stream that we want to compress, and And then we've got all these different things. We got build character frequency table. So here are our member variables. We got the character frequency table. How often do we see each character? That's going to be an unordered map from characters to integers, which would make sense, I hope. That's the character frequency table. We'll build that. That's just the number of times each character appears in our file. And then we have to hold, when we make it finally, we need the Huffman tree itself. So that's going to be represented by the root of that tree. Once we built it, we'll store it there inside of this Huffman coding class. We're going to make one Huffman coding object in our main function, and that is in compress.cpp. So here it is. It makes the Huffman coding object, and then depending on how we call the main function, it'll do one thing or another. So yeah, we've got all these things. Build the character frequency table, build the tree. So like build character frequency table should fill in this, right? Build tree should fill in this. And then getting the codes will fill in a map from characters to the string that represented that character in terms of ones and zeros. We're gonna say binary is a string of ones and zeros. That will be our output. I guess we could return a map from characters to strings, but we'll just have it be filled in. And then, yeah, I guess that's how this is going to work. Get codes is going to do that for the user if they want it. I'll give them back a character, like what is the binary representation in terms of ones and zeros as a string of each character after we've compressed it. And then if you want to actually compress the file, give it again, give the codes, and we'll make a string out of it. So there's functions that we'll call. But like that's the setup. Every piece of wanting to do anything at all with a Huffman tree, most of the implementations on this page we're going to turn into methods in the Huffman coding class. Any questions about that? That's what's going to happen. So I think that's most of what I wanted to say. Let's make it happen. So okay, that'll happen in an actual CPP file. So here, for weird reasons, we need to give a default implementation for the destructor of the base class, even though it's an abstract base class. Disgusting, but that's okay. Also, because we're going to be putting these, let's do that next. Because we're going to be putting H3 node stars inside of a priority queue, we need to know like when to prioritize one versus the other, don't we? So we should prefer popping off things. We want to make this a min heap, right? We want to pop off things with smaller frequencies. Prefer things with smaller frequencies, so we need a custom comparison class that compares H3 node stars. And it's the game that we play when we want to configure this is we want to prefer, it's always in terms of the second thing. We want to prefer the second thing over the first thing when we want to return true when we want to do that preference. Return true when we want to prefer P2 over P1, those H3 node stars. We want to do it in terms of frequencies, all right? So I would like to return true if P2's frequency, getting it with the getter, is less than P1's get frequency. That's how we prefer it over the other one. Okay? So that's going to return true. And it's always relative to the second thing. So prefer the second thing when its frequency is smaller than the first one. That's how we turn this. Like if we make a priority queue and we give this comparison class, it will prefer smaller frequencies. And that's what we want. We want to pop off the smaller ones first. Breaking ties arbitrarily. So there's that one. And then we want to do constructors. Let's do constructor, destructor. I'll just do them in order maybe. That'll work for me. There we go. So let's do the constructor, the destructor. We'll take them both just quickly. And please shout out if you have any questions. Boop. The job of the constructor should be to build the tree. We've got a method called, aptly named build tree. We'll do that. We'll just call that in our constructor. Its job, when we construct an object of the Huffman coding type, we want to build the tree for that file that we've been passed. We've got a nice method saved away called build tree that does that for us. Boop. So I want to use that. Please and thank you. Let's use that build tree. Let me have the header file over here like this. So build tree takes a file and it's going to build the tree out of it. So just ask it nicely. Build tree on myself with that file, and that's all the constructor needs to do. Just go and build that tree for me, please. Hand it off to ourselves. And then the destructor is also pretty simple. It's, all right, the one thing we're making on the heap, like this will go away. This is an unordered map. It has its own destructor. That'll be called automatically, bless you. This is the one thing that's going to be on the heap. Our big Huffman tree that's been made on the heap. And so we want to get rid of it and make sure to delete the whole darn tree. And we solved that problem last time. If we just say delete the root of the tree, the destructor for H-tree nodes and all of its child classes will do the right thing and delete the whole tree in that case. So I can just say delete my tree root. Oops. And the whole tree is gone. That's my destructor. And then we can do actual things. Okay. So build character frequency table is probably the first one. So we've got a member variable called char freq table. Let's implement the method that builds it. Dun, dun, dun. So this is Huffman codings, build character frequency table from a file. And so here, that's going to be in the body. Instead of the string, so this is what we're doing. We're using the book, right? It is the book's implementation. Here it is. Instead of a string input, we're just going to use a file because that's probably usually what you want to compress anyway. So we're taking a file instead of a string. We want to make a brand new, they call it a dictionary. That's just a hash table. Make a brand new map or unordered map. We've got a member variable saved away for that. So it's already been constructed. We have it. It's called char freq table. Okay, so that's what it is. Let's see. Yeah. Dun, dun, dun. That's what we want. All right. So the table is already our member variable, and it's already constructed. We don't have to return it either because it returns the table at the end here. We're just going to fill in our member variable. Here it is. This is the header file underneath here. We're just going to fill it in with the stuff. So I can skip this last line and also this first line. It already exists. So I want to go through every character of the file and look at that character. See if it's got an entry in our character frequency table. If it does, like add 1 to it, that's the new frequency. It's 1 more. Otherwise, put it for the first time in our character frequency table. Its count is 1. We've seen it for the very first time. Does that algorithm kind of make sense? So just shout out at me if you have any questions, but we got to translate that to C++. So, all right. I want to go through every character. So like of the table, every character of the file. So let's do it like this. So here's a character variable. While I can, from IFS, get a single character into that C variable. That reads it a character at a time and stops the loop when it's done. We want to do exactly this if statement. If the table has a key for that current character, so if char freq table, it's .count. If there is that character C exists, and so its count is bigger than 0. So if it's bigger than 0, it's exactly 1 in that case. It's either however you want to think about it. So it's definitely 0 if it's not there. You can do it backwards. So if it's not there, then put it in the table. Char freq table dot in place C count. It's got one thing. We've only seen that character C. Maybe it was the A character only once. Otherwise, we've seen it before, and let's just add 1 to its count. Character frequency table. It's got a C. I can go there and just be like plus plus. Whatever that count was, make it 1 more now. And that's me building up the character frequency table. I want to be nice and not use these because I've been good at using them in this class. I don't need curly braces for the bodies of those if-elses because there's just one line. So that's how a cool kid would write that function. So yeah, I think that is the implementation. Does it make sense to us? It's like, all right, it's filling up with that table with all the counts of those characters. Going through every character in that file. That one's happy. And then, now that we have the frequency table, we can build the tree. That's Huffman build tree. So given, so that's this one. It's a private method just for us. So the constructor calls it, right? Implement the build tree. That's Huffman build tree from the book. And it's Huffman codings build tree. There's a few differences from what's going on in the book. The book asks the frequency table to be built right then. We do this in a slightly different way. We don't have something called, we have something called table, we don't set it equal to. If we want to build our character frequency table, that's this method. Just call it on ourselves now. So maybe let's get rid of that so there's more room to see things. So we just call ourselves to build the frequency table on the file. So we've been given the file, build the frequency table on it, please. So on myself, build the frequency table with IFS again. And then now we can make our priority queue. Make a priority queue of nodes. It's a brand new priority queue. It's holding H-tree node stars compared using the smallest frequency, preferring the smallest frequency first. And that was exactly why we made this comparison class. So we'll use that comparison class as we're building our priority queue of H-tree node stars. That's the algorithm, all right? So let's make that happen. So let's make a priority queue of, oops, the way it works, what do we want in an H-tree node stars? We want to, you got to give three things. If you want to give the comparison class, you also have to tell the priority queue how you want it to be stored. How do you want that heap to be stored? I want it to be stored as a vector of H-tree node stars. That's like the normal default way. And then finally, I can give my comparison class, which is called compare H-tree node pointer. That's how I want you to compare all my nodes in the priority queue, and I'll call it nodes because that's what the book called it. Nodes. Nodes is a brand new priority queue. All right. And then I have to go through the character frequency table and add a leaf node for each character and its frequency and put that into our frequency and into our priority queue. So that's this algorithm that we drew from before. So start with the leaves only. One for every character, attach its frequency. So all right, go through then. I got a loop for every char freak pair in the character frequency table, and it's going to be a pair, right? It's going to be a character. Like there's way too much going on right now. Let's do that. Let's do a split so that we can see the header file. We've got something called character frequency table right now. That's our character frequency table we want to go through. We're going to get back a pair of character and int every time we go through it in the range-based for loop way. So you could say the type here, but I'm just going to be lazy and say auto. And let's get a reference so that we don't, let's do constant reference to whatever that pair type is. I'll just call it charfreak pair. It's got a first and a second. A first and a second, where the second thing is the int, the first thing is the character. They're mapped in that way. And so what do I want to do? I want to make a brand new leaf node every time and add it to my nodes priority queue. So nodes dot push a brand new leaf node on the heap. And it needs a frequency and then a character in that order. In our character frequency table, the frequency comes second. So it's charFreakPair.second. Then it wants the character with that frequency. So that's charFreakPair.first. So I'm just going through my frequency table, getting out the stuff I need, adding them as a new leaf node, because that's what the priority queue needs to start with, just a bunch of leaf nodes. Remember that? See how that's working? Questions about that? And then we loop. So while we've got while we have more than one thing in our priority queue, we have things to combine still. So while node's length is bigger than 1, so while nodes it's called size in C++ is bigger than 1, get the left and the right. The left is pop it once, the right is pop it again. So get two things with the smallest frequency. So if I say nodes.top, that gives me the highest frequency thing, or not the lowest frequency thing. It gives me the highest priority thing. And that's an H-tree node star, because it's a priority queue of H-tree node stars. I'm going to treat it like its base class. That's the left thing is the top. Then if I pop it, I can get the right thing. So I do that twice. The thing that's going to go on the right of my new internal node. So call them like that. And then the summed frequency is the new frequency for the internal node that we're about to make as we fuse together these two potentially character leaf nodes, potentially two internal nodes, potentially one in the other. The new frequency sum is the sum of the two frequencies. Int frequency sum equals left's frequency. I always got a frequency plus right's frequency, and it's a getter. All right, we're going to use the getter because this is not that was the only public thing we have for our nodes to tell us that. Because frequency in each H-tree node is protected. This is outside of that class. We got to use the getter. All right, and then we need to make a new node called parent. It's a brand new internal node. So htree, and we're going to treat it like its base class. htree node star parent is a new internal node. So it's a little weird looking because I'm saying new internal node and saving it as not an internal node star, but an htree node star. That's fine. Treat it like the parent. So every internal node needs a frequency and a left and a right. What do you know? I've got a frequency sum and a left and a right. There's my new node. I add that to my node's priority queue. So nodes.push, that parent node. And so each time the priority queue gains an internal node and its size decreases by 1 because I pop 2 and I add 1. It's like taking 2 steps back and then 1 step forward. Or, sorry, 2 steps forward and 1 step back. We're eventually going to get down to the case where we just have one thing left in the priority queue, and that's the fused together final Huffman tree. Right? There it is as one big internal node. The second this loop stops, there's only one thing left in the priority queue, and so that's going to be the root of my tree at that point. The tree root equals the result of all this. Like, give me that last thing. It's like it's doing it this way. Return one last pop, kind of. And that's the root of your Huffman tree. And so that is our member variable. It's called tree root. It's a little bit different to the book because of that. It's a member variable. So tree root equals, give me the top thing of nodes. Now, once that loop is complete, there's only one thing left. Give me that one thing, put it as my tree root, and I'm done. And then I'm happy. And this has completed the entire tree. Yeah. You follow it? See how it's the same as the book is saying? Same that we said in class? Just C++ified. Yeah. So we got the tree. Now what do we want to do with that tree? We got a few things. So we can get the codes for that tree. That's going to, for every character, like the A character, maybe it mapped to like left, right, right. Then it was like, that's 0, 1, 1 or something. It's like turn each character into a string that's just ones and zeros that represents the binary version of that character encoded using our Huffman tree. All right, so that's what getCodes does. And it's going to hand off the problem to getCodes recursive. So maybe we should be thinking about both of those at the same time. So getCodes and getCodes recursive. Boop. getCodes recursive. So here, Huffman coding that. Oops. Boop. So here's kind of the idea. Let's do, gosh, what's the best way to think about this? The job of getCodes is to give back, like you made this Huffman tree, for example, is to give back this idea. Like A mapped to just the left at 0. B mapped to go right, left, left. It was 1, 0, 0. There, compute a string encoded binary thing of each character. Like what is its code in the Huffman tree? How have we encoded it? What's its shortened thing? So that's what we want to build. It's a recursive idea. So Huffman getCodes is a recursive idea. Let's do that one first. I think that would make the most sense to take that from the book. That's I'm going to call that getCodes recursive in ours, and we'll come back to this later because this is what the user is going to call. We're going to deal with the heavy lifting here. So the job of getCodes recursive is going to be somebody gave us a tree, a Huffman tree. We'll use that on ourselves because somebody calls it like this. Call it from the root with an empty string and give it a brand new unordered map or something. To start off the problem, we're going to use a map so that there is some order for each character. It'll look pretty when we output it. So you give me a Huffman tree. You give me what prefix we're on right now. At the very start, there is nothing. Like we haven't added a one. We haven't gone left or right. It's like there's nothing to add yet. And then you give me a map to fill in once I get to the leaves, because then I'm at a character and I've built up a prefix to get to that character with. So you give me all those three things, and I'll fill in that map for you. So I'll check the map as a reference. So that's how this one's going to work in C++. It's a little bit different because this one's returning something. But now with that in mind, we can do getCodes recursive. It's, well, if the node is a leaf, what do we do? So we're at some node. Like we want to say it's this slide. Remember we started with Emptiness, we went left, we added 0. The prefix to get there was 0. We went left again, prefix was 0, 0. Left again, prefix was 0, 0, 0. And then when you're at children, whatever your prefix is the encoded version of that node that you got there with. Because if you went right, you added 0, 1. Like if you got to this E, your prefix would have been 1, 0. So like the recursion will get you down to where you need to be. If you're at a leaf, you have an actual string. You have a final thing for that character. That's its encoding. E was 1, 0. R was 0, 0, 0. All right. So yeah, if the node is a leaf, what do you know? If node is leaf, returns true, then that's something we care about remembering. Output, map the character in that node to the prefix we built up so far. So we've called it output right there. Let me put it on a separate line just so you can see all these things. So some people, there's so many different options that people prefer for like aligning things on multiple lines. I'll just have fun and do it this way. So those are our 3 things. 1, 2, or 3 arguments. And here now we're in the body. Sorry, if the node is a leaf, output, that map, we want to in place a new thing. We want to map a character to its binary encoding in using the Huffman tree. So map the character, so the node's character, nodes get character, because if it's a leaf, it has a character. Map that to the prefix we've built up so far. That's how it's saying. And that's just this argument. So that's if it's a leaf, we're done. That's like a base case. Otherwise, recursive case. Otherwise, go down the left subtree and the right subtree and fill in the codes, remembering that if you go left, you add a 0 to the binary encoding. If you go right, you added a 1 to the binary encoding of everything. If you go left, your prefix has a 0 in it at the end now. If you go right, your prefix has a 1 in it at the end now. That's how those get built up slowly but surely down to the leaves. So we'll do that. So call those 2 things recursively. So our method is called getCodesRecursive on nodes left. So get left. The prefix is whatever the prefix was before, plus a 0 if we went left. And then we still want to fill in the same output map. That's why we do it this way. We took it by reference so that we can fill it in no matter where we are. That same one. If we go right, that's how we get there, and we remember to add a 1 to our prefix. And that's the very simple method that is recursive and fills and gets down to the leaves in the right way and remembers what the encoding of each character was. It's beautiful. So does this method make sense? It's a function here, but we've turned it into a method. Because this is what the user wants to call. Like we need to return to them that actual map. So they call it with nothing. We do the heavy lifting. We start off the recursion for them. So here's how the recursion should start. You give it the root of your tree. It's this call here. You give it the root of your tree, the empty prefix, and a brand new map. So let's make that. So like we're going to make a map from characters to strings. That's the thing we're going to return. Those are our codes, and we're going to return that after we filled in that map by passing it to getCodesRecursive, starting from our tree's root, which is our member variable, tree root. And the prefix starts out empty, and then the codes map is what we want to be filling in this whole time. That should do it. So that's our new thing, and that's most of it. So that's getting the codes out, and then if you want to compress something now that you have the codes, you can turn your file into a bunch of 1s and 0s and see how long it was. So that's the compress method here. So you give me the codes, the mapping of each character to its binary equivalent using our Huffman tree, the compressed version. And then you give me a file. You give me a file. I will compress that file using this map. Every time I see a character, like the A character, I'll go look it up in the codes map and turn it into the binary version that we remembered. So I'll just give back a big string of 1s and 0s, which you could imagine you could do this really with like bit fiddling, bit twiddling stuff, your bitwise operations. So you can actually do binary stuff like this, and that will turn it into something real. But for now, this is good enough. Let's compress. Let's Huffman compress from the book. So, all right. Boop. So the way this is going to work is somebody gives us a file and our codes map. So we just use those things. So, okay, oops. Where am I? There. What we want to do is go, first of all, this file has been read through. We read the whole thing to get the frequency table. We want to compress the same file now. We have to say, because the file remembers that it's at the end of itself, we want to rewind that file back to the beginning. And it's these two things. You say clear to remember that everything's fine now. We're not at the end anymore. And then seek G back to index 0 of the file. You can think of it that way. All right. That brings us back to the start of the file, and now I can go through the characters of the file once again. And this is Huffman compress. Boop. So we've already built the tree in the constructor. We're good there. We've gone back to the start of the file. We've already got the codes delivered to us. Somebody passed them to us. So we can skip that one. That's how we're going to call it. The rest is just this. This is what we're going to implement. So, I don't know, just for fun, what if I copy and paste it and then correct it? So how do we turn this into C++? Yeah, string result, empty string, good. For every character in the input string, it's not input string anymore, it's the whole file. So we got to play the same game of like going a character at a time using some sort of while loop. So we'll say RC, and then it's while I can get a character into C from the file, and the file is called IFS. So we play the same game with the arguments so you can see their names, or the parameters. So while I can read from IFS into C, and it's good, then I'll do that. And then I want to add to our results string codes looking up the character C, so it's codes at C. Yeah. And then return result. We don't have to return the root. The root is already in our member variable. We also don't have to, worry about the codes they were given to us. So it's just the string. We've built up that compressed thing, which is a bunch of ones and zeros, which you could turn into binary if you really wanted to. That's what we have. And I think that is everything. Let's compress. And that should do it. Are there any questions about that one? See how it's, I mean, we're copying the book, but hopefully you can see the method behind the madness. Like we talked about all this, we drew pictures. What's going on is what we talked about. Yeah, good. So the main function is in compress.cpp. So if we get back to the terminal, we can actually compile this now. And so we've got a file called compress, and the way it works is that you give it a file that you want to compress, and you ask for, hey, do you want to give me the codes, or do you want to do the actual compressed version of that file? So let's take, I've got a file called the quickbrownfox.txt. There's the whole file. And we can say /compress with that file, and let's get the codes. And so what it did is it built the Huffman tree, the constructor, and it called get codes, which did everything, made the map for us, and then it went through that map and it's printing it out pretty for us. So it looks like space was so often in this file, like this sentence with all the letters of the alphabet, like that became 0, 1 because it was so often, and then you got vowels that are a bit shorter, like E appeared a lot, I guess. It's only 4 bits long. O is also 0, 1, 1, only 4 bits long. U as well. But everybody's been compressed in a nice way because by default every character is going to be 8 bits. At most, there's 6 here. See that? That's quite nice. I've also given you the entire works of Shakespeare. So you can do the same thing with Shakespeare. They use much more characters, like including capital ones. So let's get the codes for Shakespeare. And then you see some things are longer than 8 bits, but we still have saved a lot. Looks like new line is appearing. New line takes 5 bits now instead of 8. Space takes 2 bits now. So there's a lot of spaces in the Shakespeare file. Makes sense. Space is only 2 bits now. We save so much data. It's a quarter of the normal size. Lovely. Quotes appear that often. Periods appear. Numbers, we've exchanged space. We've saved space on spaces, for example, in periods, but we now take more space to store numbers because those appear less often. It's like Act 11, Act 12, or something. Those don't appear super often compared to other things. All our capital letters, some of them don't appear as much, like Q, capital Q. That's more than 8 bits now, but it still saved a space. Still saved a space. Like the vowels, E, lowercase e is 4 bits long now. So you better believe we've saved a lot of space by doing this. Those are the codes. You can also do, the other option besides codes was do the compression. So if I want to compress the Quick Brown Fox, it turns it into the 1s and 0s that it was supposed to be. In my makefile, I made a nice little test for us that does stuff. It's called run compress tests. If I say make run compress tests, it's going to run a bunch of stuff in a certain order. And if we do that, we can compare what we get as output with the expected output.txt file. So if I look at that file real quick, that's got everything that we did again. Like that's what the output should have been, for example. So if we look at the lab write-up, this one, we will see and this is how we can save it as a file. We want to save it in a weird way where the standard error gets mapped to the standard out as well, if you know those words. So that will have everything redirected to the file, including stuff that's not normally redirected to the file. Because if I just do it like this, without this extra weird stuff, I guess it's fine, actually. Never mind. But sometimes you see output. So just to make sure, just in case there's any errors, like it puts the errors in the file so you can see those too. So there they are. Now I've got a file called my output. That's like the output that we get from running all of those tests. Like if we don't redirect it to a file, of course, it just prints it. So we saved the printed stuff. We saved it as a file. Now we can run diff. You know what diff does now? It shows you the difference between two files. Diff expected output and my output. And if they're blank, if there is no output, that means there was no difference. And that means we can turn it in and it's going to get full credit. So yeah, that's more or less the lab. You're only going to turn in the .cpp file. So the header file that we worked on a little bit, you still need it to get like it to run on your own end and to understand it all. But just the CPP file is going to be what you turn in. It'll use the header file that we've made. So that'll work just like that. And I think that is everything I wanted to say about the implementation of the lab. If you missed anything, you'll have to either do it yourself or watch the video. Because I won't give you this code, of course. But at least we did the lab together this time. Any questions about the algorithms? All right. So that was fun. I think that's more or less what I want to say about most of that. I now have a question for you. Oh gosh, I shouldn't have closed that section of the textbook. We implemented the building of the tree method, right? Huffman build tree. I want you to think about the complexity of that. Oop, there it is. So here it is. It's in the book, and go look at it. Here it is. Here's that implementation. What is going to be the, let's see. What do you think will be the running time complexity of building the Huffman tree? All right, where, let's assume that the input, you can go to the book and look at the code. I can put it here just for fun if you want us to. Let's think of it in terms of the way we implemented it. No, I guess let's just use all this. So there's the implementation from the book, which is what we implemented, more or less. There it is. What is going to be the worst case complexity, you think, of building our Huffman tree? Assume that the file you're trying to do, the input string in this example, assume that your input file that you want to compress is of length n, it's got n characters. That's the one thing that varies, right, depending on what you want to do. And try to come up with the complexity, the running time complexity only, of building that tree. All right? So yeah, that's what I want to say. Try not to look at the next slide if you don't want to. You can write it down if you'd like. I'll open up the written nice page for us. I'll zero it out. But yeah, try to get into groups and discuss here's the code. We watched it. We know it well. We drew pictures of it. What is going to be the running time complexity, do you think? In the worst case, assuming the input size is n, of building the Huffman tree? Think about what needs to happen. Remember, for the frequency table, that was a hash table. It was an unordered map. And on, you can just pretend it's like constant time to put stuff in. We'll make that as many but like some fraction of that. Like how many letters are yeah, I guess there's only so many letters in the alphabet. A lot of things going on, but remember the picture. Think about the pictures in your mind. I didn't know what you said about this. The can't feel anything that we're yeah, no, that's like we are building a kind of tree, but we're building it. Yeah, assume it's like constant time to do stuff with hash tables, and remember it's logarithmic time to do stuff with heaps, right? Yeah, so I'll give you another minute to ponder and discuss, and then we'll talk about it together. We're talking about worst case. So worst case, every single character within the string is a new character, right? So I'm going to have to make at least that many nodes, plus however many nodes above that. Making the table is constant times their constant still. Wow, okay. All right, that's my timer. Any questions came up as we were thinking about this that I could help with? Well, let's see. No, Nice. At least one of us had an idea, so that's good. So yeah, O of n, character frequency table, go through all the characters. That's good to think about. That's gonna be the first bit. So let's talk about it. Let's talk about it together. Dun, dun, dun. So all right. We've got like a few steps, right? You got to build the character frequency table. You got to go through every character on the frequency, make leaves. Then while you got stuff in your heap, pop two things, push a new one. Okay, pop two things, push a new one. So okay, assuming the input's n characters long, and let's just for the sake of example, even though like that worst case for an unordered map really is like linear time, like it gets horrible if you have too much collisions. But let's pretend that C++ did it right and well, and it's going to be constant time to put something in an unordered map as it should be. All right, so that's what it's going to be. So let's say then that it's going to be linear time then to build a frequency table because, right? Dun, dun, dun. Linear time to build a frequency table because you have like for each character you see, you got to go like look it up in the map, see if it's there or not. That's constant time, and then update it. That's also constant time. Getting values back, seeing if that's a bunch of constant time stuff. Hash tables are great. So that's linear time total then. So it's n times constant, which makes linear. So there's that one. Let's see. And then you're going to put n nodes into the priority queue all at once, right? N nodes into the priority queue all at once. You can imagine it's logarithmic in the number of things that are actually there. So like it's constant time to put the first thing in. Then it's like log of 1 to put the next thing in, plus log of 2 to put the second thing in. For reasons that we've discussed previously, you can just kind of look past that and say that it's probably log of n to do all the insertion, per insertion. All right. So log of n to do your n insertions. So you're going to do n insertions because you got n like leaf nodes potentially. Like maybe it's possible that each of your characters is a different character, right? Because really you're going through the frequency table right now. It's possible that all of your characters are separate characters. Who knows? There's a lot of like every emoji, right? That could be things you're trying to compress right now. Who knows? So at most, worst case, n nodes in the priority queue, one for each character in the file maybe. And you're going to do logarithmic time insertion for each node because it's constant time to make the thing on the heap. You just got to push it now. Push the pointer. Logarithmic time per insertion. You're doing at most n insertions. Does that make sense? That's my analysis for that. I am sweeping something under the rug. I said something that you should be thinking about. We'll come back to it. All right, and then you're going to iterate n minus 1 times to at most, right? If you put n nodes in at most, then you're going to iterate n minus 1 times because you're going to fuse things together. It's going to get shrunk down one at a time, the size of your priority queue. And you can check size and constant time, that's fine. But then the body of the while loop to pop twice and push once, that's logarithmic time, right? Logarithmic time to do the popping and the pushing, and it's log of n, okay? And so you're going to do n minus 1 times log of n, which is n log n in the big O standpoint, yeah? Does that analysis make a little bit of sense? And then therefore, n log of n plus O of n log of n wins. And so n log n is an analysis of worst case running time, okay? So that's not horrible. But honestly, we could do better if we think about the char type. If we're going to use the char type to represent the characters, like that's everything in Shakespeare, for example. There are types for characters that need more space. Like if you want to store emojis, then you really do need a longer type. That's a thing. But like for the files that we're using, let's pretend that there's only chars that we're storing. And so chars are 8 bits. You can hold at most 256 different numbers in a character variable, right? You're going to be at most 256 different characters. And that actually changes everything. Because when you're building your frequency table, it's possible that you have a 256 size file, one for every character. That's fine. That's possible. It's still linear time to build the frequency table. You got to go through every every character of your file and do constant work. That's always going to be, that's still going to be linear. Does that make sense? You got to go through all the n characters, look them up, add them in, plus plus if you need to. That's still linear. When you think about this, that's not a problem in terms of the frequency table, but this changes drastically. Because now there's at most 256 nodes in the priority queue. Does that make sense? So that could be changed. Boop, 256. At most, therefore, 256, log 256 to insert into the heap. While loop is going to operate 255 times at most. The while loop's body, therefore, it all has to do with how many nodes were in the priority queue now, right? Which is 256 at most, yes? And so now it's log 256 on average. So it's 256, log 256 to do all that stuff. And these are just numbers, right? You can do the math. What is that? O of what? O of 1. Constant. This becomes constant time then. If you think about the fact that we only have that many characters at most, that's the bottleneck on the size of our priority queue. You see that? That is so interesting. And so now it's going to be this one plus that one. And it becomes a better analysis is to say that no, to build a Huffman tree, it's linear time in the size of the input file that you want to compress. Because the number of characters is going to be eclipsed by the size of that file. Almost certainly. Especially if you want to compress something, right? There's no real use if it was so small. So that is a better analysis, and I think that's fun. Are there any questions about that?
So is there just some cases where trying to compress a file would actually make it bigger?
Yes, absolutely. Let's see. Because you have to give along the tree as well. You have to pass the tree, or at least the table of the codes, like this thing. You got to give that to somebody, and that itself takes space. So it's possible that this whole tree probably took more. It's probably bigger than the Quick Brown Fox file for sure, almost certainly. And so you doubled the space when you could have just sent the original file. Yeah, that's a great thought. So sometimes it pays to not compress if it's so small, because you need to tell somebody got to give them the secret decoder ring or whatever. You need to get that back from them. Yeah, good question. Other questions? Because now, I want to switch gears, if we're ready, to something completely different. I want to teach you some stuff that I'm going to draw upon in a future class if you take it with me, like probably CSCI 26. If you take 26 with me, you're going to need something that I want to say here. I've got a bunch of things that we don't have time for this semester because we've chopped off way too many things with holidays and whatnot. So I want to teach you a cool part of C++ that you probably haven't seen. There are many others that you can think about, but I want to teach you about smart pointers. All right, I want to teach you about something new. It's called smart pointers, and it's pointers, but to stuff on the heap, and it's deleted for you. Like it's managed for you in a sense. It's smart about things. It knows when to delete itself. That's quite nice. So it's heap. Here's like the slogan. It could be heap memory handled for you. How do I spell handled? Handled for you. Okay? That's how you do it. So smart pointers. That's the new thing, and it lives in a header that we have not looked at yet in this class. Boop. It lives here. Dun, dun, dun. It lives in, I assume it's in other. It's called memory. Aptly named. Got a bunch of different types, and we'll talk about some of them. These ones. So those are the most important ones. So cool. This header defines general utilities to manage dynamic memory. Lovely. Let's talk about it. So what in the world is a smart pointer? You finally get to learn something that I guess this is fine. Or I guess I'll keep it there for fun. So we have been doing memory stuff. We have to start from the ground up. You guys needed to learn how to manage heap memory because otherwise you would have no clue about what's going on. That's why we don't teach Java here, for example, because Java just kind of like deletes things when it notices that you're done with it. And that makes you a bad programmer, in my opinion. So you need to know when to clean up after yourselves. We had to learn the hard way. We had to do it that way first. All right. So the real world, if you're programming C++, they've all moved to smart pointers because it's a very low overhead to have deletion managed for you. That's what they do for you. So like we've been imagining it's like the early 2000s, and at least now though, you know how to manage your own memory. But since C++ version 2011 and later, they've implemented these ideas of smart pointers into the standard library that's required to be there in any implementation of C++. We're not going to use new and delete. They don't have to anymore. If you use smart pointers, it's going to do it for you. It's going to call new for you in a fancy way. It's going to call delete for you in a fancy way if you use these new types that I'm about to tell you. So you're going to use smart pointers, and it's going to keep track of what you've made on the heap. They're going to call new for you when you make a smart pointer, and they're going to call delete for you when they notice that you don't need that pointer around anymore. That's quite nice. You don't have to worry. Like the destructor now for everything, if you just use smart pointers all day long and you don't have loops in a weird way, or I mean loops in terms of pointers pointing to themselves and like in a roundabout way. As long as you don't have that, a smart pointer will deal with destruction for you. And so like your destructor, you don't need a body anymore. You can use the default. It'll call the default destructor on a smart pointer, and the smart pointer will deal with itself. So that's lovely, even heap memory. So yeah, let me teach you the first one, the easiest one to think about. It's called unique pointer. What it does is it keeps track of something on the heap, a pointer on the heap for you that it's going to call new for you. It's going to call delete for you as well. But this is you can only have one copy of that pointer. Only one person gets to know where it lives on the heap. That's why it's called unique pointer. You don't want to share it with anybody else. If you do share it with somebody else, you have to yourself forget about it. That's what unique pointer does. Sometimes there's a case for when I just want to point it to something on the heap, and I only want to be the one who knows about it. All right, so it's in memory, and it's a templated thing. It's a unique pointer of some type T. So like a unique pointer to, for example, an int, unique PTR of an int. Think of that as secretly holding an int star. That's essentially what's happening. A unique pointer of an int holds an int star secretly. It will call new int for you, right? Because when you say new int, it gives you back an int star. Think of a unique pointer like wrapping around the idea of an int star. All right, unique pointer to an int at least. So that's how that works. And it's just going to make sure that only one copy of that object that you've made on the heap, even a primitive thing like an int, only ever exists once. All right. And so, yeah, I've got some pre-made code because I didn't know how long I'd have. I'll get out of this and I'm going to give you the rest of the code I write today. So here we're going to be in the lecture 28 folder. Here's uniquepointer.cpp. I made a file for us to look at. So include memory. And then here's how you make a unique pointer. You say make unique. There's a function in the library called make unique, and then you give any parameters to the constructor within parentheses at that point. It'll just work out. All right, and it calls new for you. All right. So let me show you those things, and we'll go from there. All right. Dun, dun, dun. So that is a thing. What do I want to say here? This is warning me. That's funny. So here you say make unique int 42. What this does is it makes a new int on the heap that holds 42. So this is a unique pointer to an int. I've called it IP, integer pointer. I'm going to make a brand new int on the heap holding 42. It's calling new for me. Right? So IP, you think of it as, dun, 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 you think of it in this way. All right. It's secretly holding on to somewhere on the heap. It's got a pointer. It's got that actual int pointer that holds 42 now. But it's also got other stuff. It's keeping track of other things potentially. Like it's low overhead, not a big deal, but that's what's going on, and it looks like I spelled heap in a way that is not legible. So this is on the heap over there. All right. So there really is a 42 living on the heap, but it's just going to deal with it for us. All right. And the way that we know that it's unique is that we cannot copy it anywhere. The way that C++ enforces this at the compiler level, only one person gets to hold and know about the address of that heap thing. they've just deleted the copy constructor, which is kind of funny. So, because that's how you copy things, right? Secretly, it's going to call the copy constructor one way or another if it's an object. And so this line will now not compile. It's like call to deleted constructor of unique pointer. So this won't compile now. If I had a line like that, I cannot copy that pointer into some other pointer variable, which is nice. Like we that controls who knows where this thing lives on the heap. So you can't do that. Only one person has it. And all of the operators that you would know and love for heap stuff, they've been overloaded. They've been implemented, so you can just say star IP to get the 42 out. That'll totally work. That's lovely. And so here, 42. There it is. It gave me the 42. That is a thing. And if you don't have something yet, you don't have to say make unique, you can just declare. And it's not going to be garbage because it has a constructor. It's an actual object. The unique pointer is an actual object. So its constructor, when you say semicolon, puts something sane inside of the pointer. You could actually get out the pointer by saying .get. Let's go there. Unique pointer. If you say .get, you can actually get that stored pointer, and then you can mess with it. Then you could copy it if you really wanted to. Then like all bets are off. But like if you really wanted to see the address, you could print it out with the .get. So there it is. The default address is null. That's so nice. But you better believe that bad things can still happen when there's null. Like it'll still try to dereference it in the star operator. Like it will still segfault. It's just in the operator star now, not like something more primitive. So that's kind of nice. So yeah, if you want to, for fun, manage memory yourself. Like you notice just for a second, I had a unique pointer. I really want to deal with the memory myself. I know better than C++ right now. You can tell it to get rid of the pointer. You can tell it to release ownership of its stored pointer. It gives you that pointer back, and then it's your job to delete that pointer yourself. It does not destroy it. That leaks memory when you do that. Okay, so that leaks memory. Dun, dun, dun. This leaks memory. That's like it's an escape hatch, but it turns it into like something else. You can put it into another unique pointer at that point. That's kind of weird like that. So that's a thing. Yeah. So let's see. How do I want to say this? If you didn't say that at least. Dun, dun, dun. I can look at the pointer for IP, and if I didn't say released, dun, dun, dun. If I didn't say released, it was just like this. The way it knows when I'm done with it is this is an object. It has a destructor. Does that make sense? The destructor of the unique pointer type calls delete for you. You see that? See how nice that is? Like it manages it, and everything else you get for free because it's a normal thing that gets destructed. All right, so that's how it works. It calls the destructor for you. It doesn't leak memory. It calls delete for you when that unique pointer goes out of scope. All right. Everything is fine. You can use star as usual. If you ever wanted to get rid of it early, you could say release, and then you could delete the released thing. Is there any other way? What about reset? Dun, dun, dun. Destroys the object currently managed and takes ownership. Yeah, probably I wanted to say reset there.
Okay.
You could say reset, and that would delete it for you and not leak any memory. But that would delete it early. It would replace it with null, which is nice and expected. So yeah, that's all happy. There's no memory leaked here. IP is going to go away. Like this pointer on the heap is going to go away at the closing brace of main because that is where this IP object gets destructed. Isn't that nice? So it just deals with it for you. If we run it. Dun, dun, dun. And then let's see. Yeah, let me do this example with reset. That would be fun. Because like it had a pointer. Oops. I think that would be better. Let me leave a note to make sure to change that for the next semester because I think I used the wrong one. Reset. There we go. So yeah, if you do it like this, let's just like get rid of it early, please. It will turn the pointer inside to be null, and it will also just delete it itself. Like it will get rid of it. If you didn't say reset, it would still get deleted for you automatically by the destructor of the unique pointer. So if I say valgrind, leak check equals full on unique pointer, no leaks are possible. And then this should also work, and it's reset that we care about here, I believe. U++. Also, no leaks are possible. Yay, and that one just got rid of it early. Like, I'm done with it now. Set it to null. But, yeah, that is unique pointer in a nutshell. It wraps around the idea of a pointer to memory on the heap that only one person can look at. Only one person is allowed to know that address, which has some good security, what's the word? It has some good security features, I think you can imagine. Like if you want to implement something where security is tight, you probably want to use a lot of unique pointers. That makes it easier to analyze that program and know that you're not actually accidentally sharing some memory values with somebody, some other class accidentally. Okay, so that's a unique pointer. Any questions about it? Just by virtue of its constructor, this make unique thing, its destructor, you could probably implement this class yourself now that you know about it, but like it's going to manage it for you. The destructor on a unique pointer, if you make it on the stack, will get rid of any heap memory that it's got inside of itself. That's a unique pointer. Though we use pointers and we copy pointers all day long, so there should be another one. And that other one is called shared pointer. All right, so there's a shared pointer now, and that's the one that most people gravitate towards because it lets you copy things, and it still knows when things can be deleted. It's wonderful. All right. So you better believe there's a shared pointer T that wraps around a T on the heap. And copying is allowed. The copy constructor lets it happen. And make shared is the equivalent of make unique. It will call the constructor. It will make something for you of that type. And now the question is, if I can have multiple pointers to the same heap object, I've got multiple objects dealing with that address, right? If I make a shared pointer to 42, like shared pointer 1, shared pointer 2, and then here's the heap over here. If I'm allowed to copy addresses all day long, I'm allowed to do something like this, right? 42. I can have the shared pointer 1, like that's the one that actually created this memory. Then shared pointer 2, I can copy that address into shared pointer 2, and it's also pointing to 42. And you better believe that the destructors of these shared pointers are going to try to delete this thing, right? What if shared pointer 1 lives longer than shared pointer 2? So shared pointer 2 destructs itself. How does it know to not get rid of 42 because someone else needs it? Do you see the problem there? That's what you need to worry about if you want to have this managed. And the answer is to use what's called a reference count. If you let yourself copy addresses, you need another member variable. You need another member variable. So every time you make a shared pointer, it secretly also, the very first time you make something on the heap, it secretly also makes a box on the heap that keeps track of how many people are pointing to this object. Let's forget about shared pointer 2 for a second. So at the very start of time, if shared pointer 2 does not exist, or hasn't been set up yet, this will point to the number, where do I want to go? 1, and that's called the reference count for this thing on the heap. There's one person pointing to it right now. Does that kind of make sense? Then shared pointer 2 comes along, you copy the address. It's also going to remember, it's also going to copy that reference count. The same place. It's going to hold on to that address, and it's also going to hold on to this address. And it's going to remember, like, oh, I'm copied. Like in the copy constructor, there's an implementation detail here. It's like, oh, I need to add 1 because I'm a new person pointing to that thing. Does that make sense? That's going to save us here if one lives longer than the other. Because now if shared pointer 2 goes away, it will just, in its destructor, subtract from the reference count. And it knows that, oh, there's still one person pointing to this thing. It's not my job to get rid of this memory yet. Does that make sense? Yeah. Shared pointer 1 comes along if it's about to go away. In its destructor, it's going to subtract from the reference count and be like, oh, okay, now there's 0 people because I'm going away. 0 people pointing to this thing on the heap. Therefore, I have to do the cleanup job. I'm going to get rid of it now. And that's how it's not going to leak memory. Do you see how, like, the constructor, the copy constructor deals with this? The destructor of this type is managing memory for us. I think you could implement this if you thought long and hard enough. That's so cool. It's so fun. So, yeah, let me show you that. Let's see here. Yeah, it keeps what's called a reference count, and that is the secret. And yeah, I just have an example of that. shared pointer.cpp. Here they are. And then I have something that I want to draw for us as well. So you better believe there's a make shared. So this makes an int on the heap, shared pointer 1. And then it has a reference count. It's called use count in C++. It knows that there's one person pointing to it at that point in time. Just one guy, SP1. Then you can copy it. Copy constructor is allowed. It's going to share the reference count and the memory. So if you go through, now you can go through either SP2 or SP1 to get to 42, of course. Star SP1, star SP2 is going to give you 42. You can update it either way. They're pointing to the same place, but they're also remembering the reference counts. That's also a separate thing. So you are trading some space for this, but it's only an int on the heap. It's not a big deal. So sp1.useCount and sp2.useCount, once they've been copied in this way, they both know that there's two people pointing to that address, them and somebody else. Okay? And that's how it knows. So if one lived longer than the other, then they wouldn't step on each other's toes. They would make sure that that 42 lives as long as it needs to, as long as there's at least one person pointing to it, as long as that reference count holds at least 1. The destructor always subtracts. Once it gets to 0, the person who made it 0 gets to do the job of deletion of that memory. So that's how it keeps things alive. It's wonderful. Any questions about that? Very cool. Very neat. And so, yeah, we could have been using shared pointers all day long. Make shared H3 node star. Right? Make shared, oh, sorry, not H3 node star. It does the star for us. Make shared internal node. Make shared child node. So that's the one. And then here's just like a pre-made example of some stuff that we can draw and talk about. So this is a more involved example that is worth talking about and drawing. So let's remember the two places where that we usually make stuff in memory. You got the stack, where you have local things with names. And then you have the heap, right? Dynamic memory goes there. So if you make a shared pointer, let me just draw through this entire application. So draw this. So shared pointer sp2 equals make string on heap. Whatever that gives back, I'll shove it into something called sp2 in main. But we have to call the function first and do stuff. So the function is getting called. It's returning a shared pointer to a string, you see. So the very first line that really runs then is sp1 equals make shared string. So sp1 is our first shared pointer, sp1, boop, just like this. And it's going to point to, it's going to make a brand new string on the heap that holds hi mom. So shiny and new, there it is. So it's going to point to that. Boop. Oh, exclamation point, of course, if we wanted it. And then it's also going to have a reference count. So it's also going to have the fact that, all right, I made that thing. By my own hands, I made this. My reference count then for that new thing is 1. That's how the make shared works. And then it's going to return that pointer. So for a split second, right, if we think about this really on the stack, it's like main, then make string on heap. This is like we're zooming in here and there's that. But also main has memory that's about to get made. SP2 is going to be the result of whatever this is. And so for a split second, SP1 and SP2 are live at the same time. Does that kind of make sense? Because it needs to copy one into the other. So that's what's going to happen. So for a split second, because SP1 is all this stuff. It's local memory, right? It's going away. But for a split second, we were copying it into SP2, the returned value. So SP2 gets made. SP2, it's a copy constructor call. So it's copying whatever was in SP1, so it's going to copy that address on the heap. It's going to copy the address of the reference count. And also the copy constructor implementation increases the reference count, marking that I didn't make this thing, somebody else did, but I'm holding on a pointer to it now. I have knowledge of this. There's a second person, whoever else is out there, notice me. There's 2 people now holding this address. Okay? That's what's happening. And so then that call to make shared thing on heap, right? This is now that call. It's going to go away, right? All of the local memory associated with that call goes away, which is SP1. So SP1 is going away. It's getting out of here. And so its destructor, what it does is it subtracts from the reference count. It notices, okay, the reference count is 1. Therefore, it's not my problem to deal with any of this memory. Somebody else holds a pointer to it. They need that. I'm not getting rid of it. All right? But I myself am gone. Goodbye. So that's what happens. And so now we're back in main. This first line has completed. Does that make sense? What's happened there? Now it's only SP2. There's only one person pointing to that heap memory, and it's SP2. And that's okay. All right, and then SP3 comes along. It's going to be a copy of SP2. So it's going to hold on to, dun, dun, dun. So now, right, originally SP1 knew about the thing. Then it was SP1 and SP2 for a short burst. They both knew about that object. And then now it's SP2, so lonely. But now SP3 is going to hold a copy as well. SP3 comes along. It's going to point to that same place because it's a copy constructor call. Point to the same place. It's going to point to the same existing reference count. Boop. And now it knows it's going to mark that, hey, somebody else is pointing to that thing. It's me. So 2 plus plus. All right. There's that. And then, I'm sorry, there wasn't an exclamation point yet, was there? So at the initial point in time, it's just hi mom without anything. Hi mom, closing brace, closing quote. And then SP2 through SP2, now SP2 and SP3 are live. There's 2 people pointing to this thing, this heap memory, hi mom. SP2, we go through that and add an exclamation point. So I'll make that a green exclamation point. That's been changed, right? Boop, there it is. Now it's been added. And then you print it through SP3, so that prints hi mom to the screen, right? You'll see that output with an exclamation point because they're pointing to the same place. And then we hit the closing curly brace of main. So now destructors are getting called for all local memory, yeah? So what happens is destruction begins, and it works in reverse order of declaration just in case the later thing used the earlier thing. So SP3 is going to get destructed before SP2 because SP2 was made before. It's like a stack, kind of. It is the stack. So SP3 is going away first, and so SP3's destructor gets called. We don't need SP3 anymore. So its destructor is going to get called, which means it needs to subtract from the reference count, see if it's 0. No. SP3 sees that there's still somebody holding on to that pointer, and it's not them. So they're not going to get rid of that pointer from the heap memory because otherwise that would be undefined behavior, right? Whoever else held that reference, held that pointer, they would see garbage at that point. So they're going to keep it around. They themselves are gone. Goodbye, SP3. So now it's just SP2, and it's also a local variable in main, and it's also about to go away. All right. So SP2 is the only person that knows about hi mom right now. It's also about to go away. So it, in its destructor, is going to subtract from the reference count. Notice that it's 0, which means nobody else is pointing to this heap memory. I was the last person. SP2 was the last person. So it is going to call the destructor, or yes, technically, it's gonna call delete on the heap memory, which maybe if it was an object itself calls a destructor. Like that's now gone because the reference count is 0. And then also the reference count object itself gets to go away because that was another thing on the heap. That was the whole point, to make it in a place that everybody could see. So that can go away now. And now SP2 has correctly deleted everything it needs to delete. It can go away. It was the one in charge of doing the job of getting rid of all the stuff because it noticed that the reference count was 0 at that point. And now nobody has a pointer to that thing on the heap. It has been deleted, and that's the whole point. Yeah? Any questions about that? It's a little weird. Dun, dun, dun. It's fun though. The one time shared pointers don't work is when you have like a circular linked list or something. You have something where somebody points to somebody. Think of it. Somebody points to somebody over here, and that person points to somebody over here, and then that person points to that person. Do you see how that's going to ruin reference counts? So think about it this way. Gosh. There are right now 2 people pointing to this node, right? Through this arrow and through this arrow. If you think about it this way, just like very high level.
Yeah.
I don't want to get into weak pointer too much. We don't have the time. But there are 2 people pointing to this place, and let's say this is how you represent it. Like you only have a pointer to this guy right now. Everybody else is through that guy, yeah? Say you delete that guy. You've chopped off this one. The reference count for that is 1 now. And you've just lost access to that loop there of things pointing to each other. Do you see how their reference counts, like this one also has a reference count of 1, Here this has a reference count of 1, now it's 0 or whatever. It goes away. Do you see how they're pointing? Because they're pointing to each other, even though I don't have access to them anymore, they are not themselves going to call destructors on anybody. They're not going to get rid of any of their heap memory because they all think, well, okay, somebody else is using me. But it's a chain. That's the one time shared pointers don't work. That's the one time shared pointers don't work because you've added to a reference count, and even though it's probably not a good idea. The way to solve this problem is to turn one of these pointers, probably the one that points backwards, to turn the one that does the loop into a special kind of pointer called a weak pointer. And that's one that doesn't add to reference counts. Because then that would have correctly become 0, and that would have deleted itself, and that would have deleted itself. That's kind of the magic there. So if you turn that into a weak pointer, this would have been like initially 1, now it's 0, and that goes away. That will correctly go away as well, because this will turn into 0 too. So a weak pointer is the same thing as a shared pointer, but it does not add to the reference count. And so you have to be careful about where you put it, but sometimes you need it. You wanted to mark this pointer as one that just kind of like completes a cycle. It's not somebody needing somebody else. It doesn't add to the chain of dependencies in the sense of like, don't delete my heap memory if that one goes away. That's fine. All right. So that's kind of all that I wanted to say about weak pointer. You can look it up some more if you would like. I won't test you on it or anything, but it's like sometimes you know some stuff, and that additional shared pointer would have ruined a reference count. And that's a problem. All right, so you can read the other things, but that's the thing. There's no make weak. You have to give it a shared pointer. It's like you're copying a shared pointer into a weak pointer. And so, yeah, feel free to look at the page for that and kind of get a feel for what's going on. Oops, where were we? Weak pointer, so weak shared pointer. You can look at some of the options that, like, here's an example of it, for example. What's happening? It doesn't change the reference count when you make weak pointers. And sometimes that's what you need. You got to cut off, like, you think of it as like a dependency cycle. You want to cut off that cycle because otherwise you won't know when things are really done being used. So yeah, that's just food for thought. I won't test you on that idea or anything, but it is necessary. Shared pointers, very useful. I hope you see though. Okay. Sometimes you run into trouble with them because they're not as smart as you want them to be. You have to be the smart person at the end and use a weak pointer sometimes. So yeah, any questions about smart pointers? Managing memory for you. It's not magical, it's just cool. It's because of the copy constructor and the constructor and the destructor of those kinds of types. They're handling things for you in a very cool way. All right? There's a lot of cool things that we could be talking about, but we don't have a lot of time for, sadly. So the last thing that I want to give you, like the highlights of these slides, if I can give them to you all, that would be great. I want to talk about lambdas. So that is an idea of a function that has no name. You can make functions in C++ that have no name, which is kind of weird. So let's do that. So here, just for a second, I'll give you an example that involves some library functions that are useful. So in algorithm, we got a bunch of cool stuff. And I saw that I was in algorithm a couple ago. So there we go. Here's a bunch of wonderful functions that maybe you haven't used before. There's a for each, for example. It kind of loops through something with iterators, and it calls a function. You pass a function. You pass the name of a function. And it calls that function on every piece of that iterator from start to end. So here's a cool example. It's like for each, go through this vector and call my function on every value. And here it is. It's printing them out. Like everything, like my function takes a value that is something in the vector, an int, and it prints it out with some spaces. Isn't that cool? It's like in one line, it's kind of like doing a loop for you. It's like, all right, apply this operation to every element of my vector. See how that's pretty useful. Sometimes you want to think of things in that way. So that's nice. For each calls a function on every element in a range. Transform does the same, and it updates the values. So transform does the same. If we go to that one, transforms a range. So where's a good example? Like, all right, here we go. Go through this vector and write the output to this vector. You can also write it to the same one. Write the output to that vector starting there and apply this operation, this function that takes a value and gives back a new value So here's the value that I was iterating through, and here's the result. Add that to a new vector. That could even be a different type, because you can add it to a different kind of vector. So transform in one line, you can be like, all right, transform this range of values using this function, get the outputs of those functions on these values, and then shove them into this thing. That's kind of neat. That's transform. Yeah, there's that. Sometimes you can have a transform that takes two things, which is kind of fun. I won't deal with that. There's a count if. I'll show you all these. Dun, dun, dun. I won't show you count. I'll show you for each and transform. But count if is also cool. Dun, dun, dun. Count if. There it is. So this one is a function that takes a range again with iterators, and you give it a function that returns true or false, and it'll tell you how many times it gave back true on each element, which is kind of neat. So here is a good example. This is a one-liner now that counts how many odd elements are in this vector. It's like, all right, go through the vector, call the isOdd function on everybody, and count how many times it gave back true. So like it took a value of the vector, gave back true or false depending on if it was odd. It's counting how many times it saw true from that function called all these values. So that's a neat way of thinking about problems. That's pretty cool. So let me show those to you. And so lambdas. Boop. Let me forget about this stuff for a second, and then we'll do it. So this is not the new thing. This is, I mean, these are new function calls, I guess. Let me show those to you. Boop. So we've got dun, dun, dun. The vector v holds 1, 2, 3. I can say for each value in my vector from beginning to end, call printInt on each value, please. And printInt takes an int, does nothing, and it prints that value. So here it is. I'm calling it, and it's printing 1, 2, 3. That's one line. You can kind of read it very quickly. You don't have to see a loop. It's kind of nice. It's doing the loop for you. Then I do a new line, and then transform is kind of like for each, but it like can write to somewhere as well instead of just reading and using the values like void. So transform, take the vector v, write back to the vector starting at that same spot where you started from, and call inc, a function that I've made called inc that takes a value, gives back it +1. So that's just like you can very quickly see, like that's changing the vector to increase each value by 1. And here I am printing it again. You better believe from 1, 2, 3 became 2, 3, 4. See that? That's kind of cool. So you pass the name of the function, it calls it for you. That's neat. You're passing the function itself. So that's a very powerful thing that we don't talk nearly enough about in this class. Maybe in a future class you'll get to hear more about that. But the problem here is, I guess we use for each twice with the same function. Sometimes it's silly to be like, all right, pretend we didn't do that one. Sometimes it's very silly to be like, all right, I need to make a function now with a whole name. To like, I need to put it out here, and like, I just need to use it once for one call to for each. I just need to use this function one time for one call to transform. I got to make this function though. Everybody gets to see its name now. Sometimes that's a bad thing. Like that's just more things in the namespace. That's just like it's a lot of wasted effort, right? I gotta like move away from where I wanted to use that function in the for each call. Like I gotta change where my editor is right now. Like there's a lot of like it's a lot of pain just for this call, for example, just for this call to happen on a function that I'm only using once. Okay, gotta move around, put it somewhere, give it a name. There's an answer. It's called a lambda. A lambda, the reason it's called lambda is a very long story that I don't have time to get into, but it's a way to make a function we call it an anonymous function. It's one that does not have a name. You can make it inside of another function, and even. So a lambda in C++ creates an anonymous function. It has no name, and here's the syntax. There's fancier things you could do, but here's what it looks like. You say this. Boop. This is the code. You give 2 square brackets. Sometimes you put stuff within the square brackets. We're not going to deal with that. And then you give the parameter and the body. There's no name anywhere. See that? That's a function. It's like that. This is a function that takes a value x and prints that x. See that? You just read it off. It has no name though. But you see what it does very, very clearly. It needs its argument, of course, to be called something. You can pass that inside of your calls. That can replace you having to go make a print-int function that's separate and move around and get there and come back. So instead of this for each, I could turn into this for each now with that knowledge. For each, all right, every value from v from beginning to end, call this function right here on it. You're passing the function, you're making the function inside of the call. Isn't that cute? That's so weird, but cool. You didn't need a name for it, just like that's what I want you to do. Apply that function, please. It doesn't even need a name to every value of v. Question? Yeah.
If it's not void, do you just put the return type before?
You don't even need a return type. It will infer that return type. Yeah, good question. You don't need it because when you say return, hopefully, C++ should be able to figure out what type you meant. It's like it's auto all day long, kind of implicitly here. That's a great question. Yeah, it just kind of figures out your return type as well. Sometimes you could get more specific, but that's a bit more complicated. So yeah, where is there a good place to talk about lambdas here? There's not really even a... It's part of the language and not part of a library is the problem, so I can't even direct you to a documentation page here, I don't think. Yeah. Can I search for lambda? What does this have? There's probably a tutorial here. Lambda function C++. What do we got? No, these are just forum entries. That's kind of funny. Maybe in a tutorial somewhere, but yeah, it's going to infer the type for you. And so here I am with transform again, because this type needed to be an int return type, right? It returns a number. Now I'm doubling it, times 2 instead of +1. This is a function that doubles its value, and it's just C++ can infer that it's going to be of return type int. And it has a lot of context clues as well. Like if you're writing back to the vector, you need to know that the value that this must give back must be a value that vector can accept as well. So like it has a bunch of places where it notices what the type should be, and usually that's enough. That's a great thing to be thinking about though. So this is going to print it again. This is going to double the values. It was what, 2, 3, 4 now. So it's going to be 4, 6, 8. And if we print them again with this line, like all right, for every value in the vector, call this function that takes the value and prints it, we should see that change. So it's just it's a time saver in a sense. You gain nothing but time when you use these. All right, it's useful to have them. You could have made another function and gave it a name, but you've saved some space that way. So just like we noticed, it was kind of silly to have to go through the effort of making a brand new function. A lambda just lets you have a function with no name. You can write it on the fly in the body of the function, the call to the function you'd like to make. Give it the function there. That's really cool to think about. So yeah, that is lambdas in a nutshell. Any other questions about those? It save us some time. Quite powerful. All right. With that, I think that's everything I wanted to say for the day. There's a lot of cool other things that you can do with C++. Feel free to ask me about them. But those are things that I think are very important that you will need for a future class. You'll definitely see those again. So yeah, I think that's all that I wanted to say. Any last questions about anything that we went on the recording?
Could you make a multi-line lambda for whatever reason?
Oh, sure. Yeah, it's C++ doesn't care about white space. It'd be like, this could have been like that. Like if x is less than 42, do that. Else return x plus 1. Not a problem. Yep.
Like you obviously don't want to get too crazy.
It looks it looks a little weird. You could there is a way to like save it away. This has a type. If you think about it, I just have no easy way of writing that type. So like this could be f, and you could be like auto f equals that, and then it looks a little bit more clean in that sense. Like that's a possibility as well. If you need it quickly somewhere, you want to use it twice, but then you've given it a name. It kind of defeats the purpose. So it's usually for quick things, but you could use it for longer things like that too. Yeah. All right, good questions. So let me stop this video.